Good morning everyone and welcome to today's webinar. My name is Keira Proctor and I'm the Managing Director here at the A. Proctor Group Limited. This is webinar number 13 in our series and we've been running these since April, covering a wide range of construction topics from across the industry. So if you've missed any, you can go back and view the full series here on YouTube or through our Learning Hub at www.proctorgroup.com. You can also now book in for online follow-ups with our team, should there be anything specific you'd like to discuss in more detail or a project you need assistance with. All the details are up on our website. Today, we're going to take a look at pitched roofing design and what strategies we can adopt to manage the movement of air and moisture to ensure our roofs are both energy efficient and free from condensation. We'll start out with a look at BS5250, the Code of Practice for Moisture Control, and how it relates to roof design and the building regulations, and some of the roof types it introduces. We'll then look at the physics and design influences in more detail, and how roofing practice is adapting to meet the changing nature of these challenges. Since the introduction of Roof Shield air and vapour permeable underlay membrane back in 1996, we've been involved in all aspects of pitched roof design, from working to build acceptance on non-ventilated cold pitched roofs to contributing to technical standards addressing wind uplift. Throughout this, we've based our approach on testing and experience gained across all types of roof in the most challenging conditions across the world, building both the knowledge and the technology to meet whatever problems the site may pose. The starting point for successful roof design must be keeping the building dry. The BS5250 standard, formerly the Code of Practice for Control of Condensation, but now in its draft 2020 edition for Management of Moisture, covers all aspects of keeping buildings dry. The 2020 draft is currently open for consultation until September, so whilst we'll base our overview on the 2020 text, bear in mind there might be some changes to the detail after the consultation is complete. Of course, we'll keep updating our guidance to reflect the changes as they happen, so if it's of interest you can sign up for updates via our Learning Hub or subscribe to our YouTube channel and be notified of that straight away. The building regulations across the UK and Ireland all base their moisture control guidance for roofing on BS5250. Approved Document C in England and Wales, covering site preparation and resistance to contaminants and moisture, the Scottish Section 3 Environment, Northern Irish Technical Booklet C and Technical Guidance Document F in the Republic of Ireland all reference this guidance. This means that unlike, for example, energy performance, moisture control practice in roofing is relatively similar across all four sets of regulations. There are two main types of moisture that roofs of all types must control: moisture from internal sources, vapour and condensation, and moisture from external sources, rain and snow. External moisture is assumed to be primarily dealt with by the external weatherproofing once the building is complete, but in order to provide a secondary layer of weather protection, roofs are fitted with an underlay membrane beneath this outer layer. These underlay membranes contribute to the performance of the roof systems in a variety of ways. Firstly, they provide a degree of resistance to wind uplift forces, and the methodologies for calculating these forces and specifying an appropriate outer covering are detailed in the BS5534 standard. Outer coverings such as slates and tiles are not a continuous homogeneous layer, so they're susceptible to moisture being driven through them by wind. An important function of the underlay is therefore to ensure this wind-driven moisture does not penetrate into the structure of the roof. The water resistance characteristics of the underlay should be sufficient to allow it to also function as temporary weather protection for a limited time until the outer covering can be completed. Related to this, the membrane and any supporting structure for the outer covering, such as battens and counter battens, must ensure this moisture is able to run off into the gutters. Lastly, the underlay must function as part of the roof system to limit the potential of damage to the roof fabrics caused by condensation from internal sources. How they do that varies depending on the characteristics of the underlay. BS5250 defines two primary types of roofing underlay and a third subtype. All these types are considered suitable for the role of secondary weather protection, so the main differentiation is in their characteristics regarding vapour and condensation. HR underlay. Membrane with water vapour resistance SD greater than 0.05 metres. 0.25 meganewton second per gram. This definition covers traditional bitumen roofing felts, such as the old BS747 Type 1F felts that were a staple of tiles and slated roofing for many years. The BS747 standard has since been replaced by EN 13707 for bitumen felts. HR underlays can also be plastic sheets of various compositions, and performance criteria for these are given in EN 13859-1. The definitions and characteristics for underlays. The main characteristic of HR underlays is that they are impermeable to water vapour. This high vapour resistance gives them the name. In contrast, LR underlays are defined in BS5250 as membrane with water vapour resistance SD not exceeding 0.05 metres, 0.25 meganewton per gram. LR in this case being low resistance to the passage of moisture vapour. The EN 13859-1 standard also covers the performance criteria for LR underlays, which are typically composed of polyethylene or polypropylene. The 2020 draft of BS5250 for the first time acknowledges a subtype of LR underlay, the air permeable LR or APLR underlay. Membranes of this type, such as our roof shield, allowed the passage of air as well as moisture vapour, and we'll move on to discuss the implications of that, along with the differences between these underlay types next. BS5250 defines 4 classes of pitched roof constructions, with the pitched roof being a roof over 10 degrees of pitch but less than 70 degrees. Cold pitched roofs. In this type of roof, the insulation is being placed horizontally across the ceiling ties, with the loft space and the structure of the roof being out with the building's heated envelope, hence cold. This type of roof typically uses fibrous quilt insulation, which is both air and vapour permeable. Warm pitched roofs. In this roof type, the insulation follows the pitch of the roof, either between the structural members, over the top of the structure, or a combination of both. This leaves the enclosed space under the pitch as part of the heated envelope. In warm pitched roofs, it's much more common to see the use of rigid foam insulation, which tends to be more vapour and airtight than fibre insulation. This is primarily due to the thickness of insulation required to meet thermal standards. However, there's no fundamental reason permeable insulation types cannot be used. Hybrid pitched roof. This type of roof, also known as a room in the roof, has a mix of horizontal, vertical and inclined insulation. This means some parts are cold roofs and some are warm, with a corresponding mixture of insulation types commonly used. The term hybrid warm roof is sometimes used to describe a roof with insulation positioned both between and over the roof structure. However, BS5250 does not use that particular designation. The various junctions between the horizontal, vertical and inclined sections found in this kind of roof, they also pose additional challenges when it comes to detailing and specification. Structural insulated panel roof. SIP roofs use panels which combine the supporting structure and insulation layers into a single panel. Typically, these panels are comprised of a rigid foam insulation and timber sheeting like OSB or plywood. All these component parts are relatively air and vapour tight. The BS5250 standard gives detailed guidance specific to each combination of roof type and underlay type to ensure the response of the roof system to moisture is within acceptable limits. A roof that cannot adequately deal with moisture is susceptible to a variety of negative effects, from mould growth to structural damage and weakness. These prescriptive roof types have been developed based on a range of design criteria which must be balanced and managed. These constructions should not, however, be considered as interchangeable, as a variety of factors can influence the performance of the roof system. Vapour drive through the roof structure. This is influenced by the internal and external environmental conditions present on the specific project. In the UK and other heating climates, where buildings are heated more often than cooled, this will typically be from inside to outside. The level of vapour drive is determined by the building type, use and occupancy. A large, cool, low-occupancy building such as a warehouse will have a low vapour load, which something like a swimming pool, which is typically much warmer and more humid, will have a correspondingly higher moisture load. Off-site construction such as timber frame or SIP buildings will also tend to have lower moisture loads as there are less wet trays to dry out, and the building is usually wind and watertight earlier in the construction process. This construction moisture can lead to significantly higher condensation risks in the short term after completion. The vapour drive present determines the overall condensation risk that will be present, and as such is the start point of the hygrothermal assessment of the roof's performance. Airtightness of the roof. The airtightness of the overall roof construction, as well as the individual components, is also an important influencing factor. Whilst the vapour drive present in a project establishes the question of what condensation risk is present, the air leakage rates involved begin to help to shape the best answer. If the energy performance assessed in SAP or SBEM calculations require a low air leakage rate, that may influence the choice of roof construction or the components specified. Some types of roof can achieve lower air leakage rates more easily, particularly if extremely low air leakage rates such as those found in passive homes are required. Ensuring the transfer of warmer, more humid internal air is limited is also important, as air leakage can transfer moisture directly into colder areas, leading to localised moisture and condensation. Similarly, the air permeability of the outer covering must be considered, as roofs with continuous coverings such as metal sheets will have significantly different hygrothermal performance from discontinuous roof coverings like tiles or slates. Insulation specification. The dew point temperature associated with roof design is the point at which the warm, moist internal air cools sufficiently to lose its ability to carry moisture. This is the point at which liquid condensation will form. The location of the dew point within the roof structure is therefore a critical factor in assessing the performance of the roof. As this is influenced by both the temperature gradient and the vapour drive, the specification of the insulation has a significant effect. As the levels of thermal insulation increase, the outer layers of the roof will become colder with correspondingly higher condensation risk, all else being equal. Conversely, a more vapour-resistant insulation will limit the quantity of moisture able to reach these colder areas, lowering the risk. Achieving a good understanding of the hygrothermal performance of the insulation is important, as part of the role of construction membranes in roofing is to help balance these characteristics, limiting the risk of harmful moisture issues. Without good information and solid specifications for the thermal envelope, ensuring vapour control layers and underlays with the correct performance characteristics are chosen for the project can be difficult. Insulation and wind washing. Wind washing describes the process of weather-driven airflow inducing additional heat transfer through the insulation layers. In extreme cases, this airflow can also affect the dew points by moving colder air further inwards. Although this issue is more prevalent with permeable fibrous insulation, it's worth bearing in mind that simply friction fitting rigid vapour and airtight insulation boards between structural members may not be convection tight. If the joints and interfaces around rigid boards are not sealed and tolerances tightly controlled, there may still be gaps allowing both wind washing and convection-driven airflow around the board, reducing thermal performance and introducing additional moisture loads which will not be accounted for in the hygrothermal design. Comprehensive weather protection. A successful roof design must, of course, provide weather protection, and this is true not just throughout the lifetime of the building, but also during construction. That the outer roof covering must be able to resist extremes of weather is an obvious consideration, but in such extreme conditions, the performance of the secondary weather protection measures is also important. In the event of storm damage to tiles, slates or ridge tiles, having a robust and durable secondary layer to protect the roof until repairs are completed can be the difference between a relatively simple and limited repair and something far more disruptive to the building's occupants. Under such conditions, another aspect to consider is how wind-driven rain or even snow can enter a roof structure. Roof ventilation, if specified, should have openings carefully designed and positioned, such that rain and snow cannot enter the roof space or saturate insulation and roof timbers. Ensuring all parts of the roof structure can properly resist wind loads without damage is also important. As with many aspects of roof design, this may have a knock-on effect on other parts of the specification. If, for example, a particularly exposed location requires the use of additional wind bracing or sarking boards, or necessitates changes to the specified outer covering, this may require additional or different condensation control measures. Escape of moisture. As well as preventing the ingress of moisture from external sources, The properly designed roof system must enable internal moisture to escape and the building as a whole to dry out. This not only means ensuring condensation problems are mitigated, but it's also important in ensuring acceptable indoor air quality is maintained. This necessitates a good understanding of the hygrothermal properties of every layer from inside to outside and ensuring specifications which are designed and modelled remain fixed through to completion. There can be substantial differences in the performance of apparently similar materials, which product literature and different test methods do not always make obvious. While CE marking and the Construction Products Directive have gone some way to clarifying and standardising testing and the presentation of information, third-party certification specific to the proposed application remains the most effective way to ensure design criteria are met. Roof ventilation. Finally, we must consider the ventilation provided in the roof, or not. Whether or not roofs and lofts require ventilation has been the subject of a long-running but now largely settled debate across the industry since vapour-permeable underlays first gained mainstream acceptance in the 1990s. Traditionally, roofs of all kinds required ventilation to ensure moisture could escape, as bitumen felt underlays did not allow moisture transfer to any significant extent. Whilst there's nothing wrong with this approach and it's been used successfully for a very long time, as buildings become increasingly well sealed and moisture loadings increase, it's not always the optimal solution. This is particularly the case where complex roof shapes and rooms in the roof are present, creating the potential for dead spots where air cannot properly circulate, leading to a localised damp and mould. If not carefully designed, the pressure drop between a ventilated loft, particularly if ventilated at the ridge only, can set up additional suction forces on the ceiling, drawing both heat and moisture from the habitable spaces below. There's also the potential for issues arising from the ventilation openings themselves, which, if they can let moisture out, they can also let moisture in. If not properly designed, then these openings can allow the ingress of windblown rain or snow, and if not correctly installed, they may not provide the design airflow rates on which a dry roof depends. Ridge vent systems may also be more susceptible to moisture ingress during construction, as there may be an opening present at the ridge even once the underlay is in place. Finally, any items stored in the loft may block vents, or homeowners may not fully appreciate the importance of this airflow and block up the drafts to warm up the loft. Any subsequent loft conversion may also be complicated by the need to maintain good airflow. With more people currently looking at their options to work from home than ever before, home offices are being created in lofts. Whether done properly with a building warrant or on a more ad hoc basis, it's likely to be increasingly common, making a robust and fail-safe hygrothermal envelope design more important than ever. Taking all these factors into account, the BS5250 document offers various solutions dependent on the roof configuration, underlay type and permeability of the outer roof covering. The first factor to consider is the air permeability of the outer covering, as if this is not permeable, then some degree of ventilation will be required. In most cases, this requirement to ventilate will apply to coverings such as metal sheeting. Slates and tiles, for example, usually offer sufficient air permeability. In some specific situations, such as where wind loads may be particularly high or where traditional Scottish slating practice is being used, there may be sarky materials present on the roof. In such cases, it's always a good idea to check what effect the specific sarking type has on the ventilation requirements for that roof, particularly if reduced or no ventilation is proposed. If ventilation is required, this typically consists of ventilated batten and counter batten space directly under the outer covering. This is a separate consideration from ventilation of, for example, the loft space, although if the loft space is ventilated, it's usually not necessary to ventilate the batten space too. The first of the roof types we'll consider is a ventilated cold roof. This is the traditional form of pitched roofing used all over in the UK and is historically the standard against which more modern alternatives are judged in terms of condensation risk and timber moisture contents. The guidance on acceptable ventilation for loft spaces is given in section L5.5 of the 2020 draft document and in table L2. In every case, airflow paths within the roof should be a minimum of 25 mm deep and openings protected with a mesh to prevent the ingress of birds and insects. For a simple roof of less than 10 metres eaves to eaves, vent openings at the eaves only will be sufficient, but for more complex or larger roofs, additional high-level ventilation might be required. The requirements in Table L2 are broken into 4 classes. For roofs of 10 to 15 degrees pitch with an HR underlay, ventilation opening of equivalent area to 25 times the longest horizontal dimension of the roof in millimetres should be provided. In roofs between 15 and 75 degrees, this can be reduced to 10 times the longest dimension, with all opening area requirements being in square millimetres. If the underlay specified is of an LR type, these requirements can be reduced further depending on the air permeability of the ceiling. A normal ceiling with an air permeability of 300 mm squared per metre square requires an opening of 7 times the horizontal dimension, whilst a well-sealed ceiling conforming to BS5250 with a permeability not more than 30 mm squares per square metre can reduce this to 3 times the horizontal dimension. A further option where the ceiling is well sealed is to have ventilation at the ridge only, equivalent to 5 times the longest horizontal dimension. It is not clear, however, how effective this type of ventilation is, given no airflow into the loft is possible through the well-sealed ceiling assembly or the airtight underlay. Given the various categories and differing guidance for ventilation, and the lack of clear specification advice for more complex roof types and shapes, a simpler option is often to omit the ventilation altogether and rely instead on the vapour permeability of the underlay to remove moisture. Where an airtight LR underlay is specified on the roof, the BS5250 standard does not directly address situations where ventilation is reduced below the levels given in L5.5. However, if the underlay membrane is covered by appropriate third-party certification, it may be permissible. In this case, the vapour drive from the heated space is sufficient to drive moisture out of the roof space. In practice, however, membranes of this type can struggle to deal with the elevated vapour loadings during the drying out period, which may require the use of dehumidifiers in the building in extreme cases. There's also a good number of airtight LR membranes on the market, and whilst it might appear that they're all reasonably interchangeable, there can be differences in the specifications that might cause problems if any special conditions in the certification are not adhered to. One way such uncertainty can be avoided, however, is to use an air-permeable membrane. The inclusion of such membranes as a specific construction type is one of the principal additions in the 2020 BS5250, and this type of roof requires no additional ventilation. The particular advantage of this type of underlay, referred to as air-permeable, low resistance or APLR underlays, is that in addition to allowing vapour to escape by diffusion, they also allow a degree of airflow to boost the transfer of moisture vapour. Membranes that are used in this type of construction must meet specific criteria to ensure that no problems arise. They must have an air permeability of not less than 6 meters cubed per square metre per hour at 10 pascals when tested as required by BS EN 13859, parts 1 and 2. And also a vapour resistance not greater than 0.07 meganewton seconds per gram, or SD 0.014 metres, when tested to BS EN ISO 12572, method C. Membranes meeting the specification can, however, be used in all circumstances with no ventilation, regardless of the size and shape of the roof. They also do not require a well-sealed ceiling, making this type of underlay a great choice in refurbishment applications, where the precise ceiling specification may be unknown. Taken together, these factors make APLR underlays which meet the performance criteria the simplest solution to address condensation in cold-pitched roof applications, and the only solution that can be specified across multiple projects with no changes. In a warm roof construction, the lack of a large cold void in which moisture can collect makes the moisture control a little simpler, but care must still be taken to ensure the correct specifications are followed. Warm roof constructions are those where the insulation follows the line of the roof from eaves to ridge. The spaces within the roofing structure itself are within the heated envelope of the building. In roofs of this kind, ensuring convection tightness is important, and this can typically be achieved either through the use of a dedicated vapour control layer on the warm side of the insulation, or by using insulation that's itself convection tight, such as sealed foil-faced rigid foam. This convection tightness ensures moisture-laden air cannot bypass the insulation into colder areas of the roof. It's also important with this configuration of roof that any moisture passing through the outer waterproofing layers can drain properly. This may occur where there is damage to slates or tiles, or where wind-blown rain passes up under the outer covering. If slates or tiles on battens are used on the roof, there must be a gap under the battens in order to ensure this drainage. Where possible, this is usually achieved by draping the membrane between the roof timber in the same way as in a cold roof. However, in this type of roof, the underlay may be fully supported on the insulation layers, which can be placed over the rafters, not just in between. If the membrane cannot be draped, it may be necessary to use counter battens to introduce this gap, similarly to if ventilation were to be required in the case of an airtight outer covering. As with cold roof constructions, warm roofs with impermeable HR-type underlays will always require ventilation below the underlay to ensure the escape of moisture vapour is facilitated. This is in addition to a vapour control layer at ceiling level. The depth of the ventilated void between the insulation and the underlay should be a minimum of 25 mm deep, plus the maximum allowable underlay drape of 15 mm, if applicable. Ventilation openings must be provided at high and low levels, with 25,000 mm² per metre at low level and 5,000 mm² per metre at high level. Openings should also be provided at any features like dormers or roof lights, so the ventilation is unobstructed across the entire roof. As with cold roofs, this can be simplified by using an LR underlay. In the case of warm roofs, this allows the ventilation to be removed provided the internal layers are convection tight. If this can't be guaranteed, or if the outer covering is not air permeable, then ventilation would be needed. In a purely warm roof situation, where the insulation follows the pitch of the roof from eaves all the way back to the ridge, the lack of large voids in the roof means there is less benefit to the use of an air permeable underlay. This correspondingly makes this type of roof a great choice for buildings where low air leakage rates are a priority. This allows the air tightness of the roof assembly to be maximised, in turn lowering the air leakage rate of the building as a whole. If we extend this principle out to the building as a whole, an airtight warm roof construction can be easily integrated into a wall assembly with an external air barrier membrane. We've covered these types of membrane like our wrap-tight in previous webinars, but in a roofing application, this can simplify achieving a good airtight interface at the wall and roof junctions. When internal membranes are used to control air leakage, there are numerous penetrations that must be sealed to provide an effective airtight layer. On the outside of the building, there are far fewer issues of this nature. Using a membrane such as wrap-tight across the roof and walls of the building means this air barrier layer can simply be wrapped around the entire envelope, with a roof membrane seal onto the walls, limiting any awkward detailing where internal air barriers must negotiate structural members and junctions between floor and roof elements. In a warm roof situation with a convection-tight insulation, this provides the optimum balance of air and moisture control while simplifying the construction process and thus limiting defects and remediation works. This in turn allows very low air leakage rates to be used at the design stage, allowing energy-efficient buildings to be constructed without resorting to excessive insulation thicknesses in the walls and roof. Hybrid roofs. This type of roof construction combines both warm and cold roof elements and is sometimes referred to as room-in-the-roof construction. In this type of roof, there is a mix of cold roof voids, usually at the eaves and ridge, with a section of inclined insulation, sometimes called coombs, in between. Because of the different hygrothermal characteristics of warm and cold roof constructions, this type of roof poses some specific challenges. If, for example, the roof voids require ventilation, then additional mid-level vent openings may be required at the top and bottom of the inclined sections. This might be the case even if airflow can be provided through the combed section, as it may be difficult to design in dependable air movement under all weather conditions. Achieving a reliable convection-tight air and vapour control layer can also be difficult in this type of construction, as not only must service runs be sealed, but the actual junctions between the vertical, inclined and horizontal structures must be addressed. The simplest way to overcome this is often to run the insulation from eaves to ridge, making the roof entirely warm, particularly if it's part of an overall design strategy focusing on low air leakage. However, if this is not possible, for example, when refurbishing an existing roof, another option is to specify an air-permeable LR underlay, which will greatly simplify the entire construction, as ventilation will not be required into large roof voids. When considering the correct roof type and underlay type, the effects on the overall energy strategy and anticipated air leakage rates should be considered very carefully. Whilst air-permeable LR underlays clearly present the most effective solution to ensuring moisture can escape from a roof structure, this does make the sealing of an internal air barrier, be it an air and vapour control barrier membrane or a well-sealed ceiling, of considerable importance. Whilst it may be tempting to consider an airtight LR underlay a good step to reduce the air leakage, such membranes will often require a degree of ventilation, such as the ridge-only openings. In practice, this means an airtight underlay does not necessarily mean an airtight cold roof. If the ceiling or air barrier requirements are more or less the same either way, an APLR membrane such as our roof shield present a far simpler, more reliable and fail-safe means of ensuring condensation risks are mitigated in cold and hybrid roof applications. A more fundamental consideration is the general suitability of cold roof constructions in buildings where air tightness and energy use are the primary focus, such as passive and low-energy homes. We've discussed these types of homes and also the modern methods of construction used to build them in some of our recent webinars, so there's a lot more information to go back and review, either at our Learning Hub at www.proctorgroup.com or here on our YouTube channel. In terms of today's discussion though, the simplified answer is to consider that for very airtight buildings, a warm pitched roof with an external air barrier layer presents a far more optimal solution. This is particularly true where this air barrier solution is also applied to the wall constructions. Using a continuous layer of our wrap-tight external air barrier around the entire structure will facilitate the passage of moisture, whilst providing an effective air barrier. Being fully self-adhesive, the material also bonds to the substrate, reducing the likelihood of damage from extreme weather conditions during construction. It also makes for a simplified installation process compared to mechanically fixed external membrane. It also reduces the sealing requirements around internal surfaces. In buildings constructed using cross-laminated timber or structural insulated panels, the wrap-tight can be used to seal the panels immediately after erection, providing weather protection and a wind and watertight envelope to begin internal works. It can then have additional insulation fitted externally as necessary, providing a flexible and adaptable construction method that can accommodate a variety of thermal performance targets. So hopefully that's given a good foundation on some of the factors involved in the hygrothermal design of pitched roofing. Let's now move on to the Q&A session. Well, good afternoon, everyone. I'm so used to saying good morning because we've had our webinars at 10 a.m. Every single Friday or every second Friday towards the latter stages of lockdown. And for the first time today, we had some connection issues, which was disappointing. I'd like to pass the blame, but I believe something to do with Sky. So anyway, that aside, thank you very much for joining us, those who could make it. Getting a little bit of feedback there. I'm not quite sure what's going on, but anyway, so moving on. I hope you're all doing really well. And that, you know, if you're in Aberdeen or one of the other areas that's slightly locked down, that you are enjoying coming out of the lockdown period. As you know, we will stay on and try our best to answer all of your questions. So please ask them here on YouTube in the chat feed, or you can email us at webinar@proctorgroup.com or DM us on Twitter at proctorgroup as well. On our dedicated webinar page on our website, you can request a sample pack regarding the materials that were discussed in this particular webinar. And you can also request your personalized CPD certification. There on that page as well, you can also request a meeting with one of our staff and look over your CAD drawings, talk about your project, and just generally touch base with us if there's anything else you would like to know. Our next webinar will be at the usual time of 10 a.m. And it's on Friday, the 21st of August. So a slight revisit on a topic we've done before, and it's all about aerogels in building refurbishment. So again, a really interesting material, very thin insulation with very interesting characteristics. So I hope you can join us for that. You will receive a follow-up email. If you've been with us before, you'll know what to expect. You will receive a follow-up email which has a link to a replay of the webinar, which again encourage you to circulate with your colleagues and anyone else you feel may be interested. And on that, there'll be a short survey So we do read all the surveys, I read them personally, and we circulate them around the team and make sure that we use any feedback constructively to help shape or make our future webinars better. So I will introduce the technical panel very quickly, and then we already have some questions from this morning that were sent in advance of the first, when the webinar was meant to be, and some good ones on the feed. So we will just start. So Ian, if I can just check that everything's working fine for you.
Yeah, good afternoon, everybody. Thanks, Keira.
Good afternoon. Good. And Pam, have you got your gin and tonic? Good afternoon. Oh, you're muted. Sorry, Pam.
I was trying to be clever there and use the space bar temporary unmute, but it wasn't working. No, I've left the gin and tonic in the fridge for afterwards.
Good. You're not alone. You're not. And Sue, are you okay today?
I'm good, thank you.
Good, good. So Ian is our technical director, and Pam and Sue are both in the technical team working with Ian. So between them all, there's a raft of experience and a lot of years in the construction sector and with Proctor Group. So a lot of experience and hopefully able to answer all your questions. So I'll just start with some of the ones that have come through on the YouTube feed. If we start with James McGregor, Pam, if I can direct this one to you, please. He said, I am building a new roof and incorporating PV units into the tiles. Do I need to ventilate the roof?
Okay, yeah, I mean, we're seeing quite a few more projects coming where PV units, photovoltaic units are being used on the roof. There's some similar considerations to take into account with these as you would with the outer covering. So we're talking about whether that outer covering has enough air movement, air permeability through it to allow moisture to disperse the atmosphere. If the outer covering is too airtight, i.e. doesn't meet the requirements in BS5250, then you would probably need to incorporate ventilation into the batting cavity. So that's between the membrane and the outer covering. And this is certainly the case at the moment with some metal sheet roofing, close fitting fibre cement tiles, that sort of thing. If there is sufficient air movement, i.e. it's been tested to Annex L of BS5534 and complies with 5250, then you won't necessarily need to provide any any additional ventilation underneath that. But you're really wanting to make sure that you don't have any risk of moisture condensing in the air or causing rot to the timber, etc. If that can't be achieved, then you might have to look at doing something like ventilating within the actual roof space itself, but really give the technical team a call and we'll be able to look at that. Because there are some considerations around PV units that you've got to take into account, like exposure of the membrane, influence of heat, that type of way it's mounted to the roof. So really any PV units situations, give us a call and we can discuss it on a merit be case by case.
Yeah, it's something we're seeing a bit more of generally in the sector anyway. So yeah, absolutely good. Okay, thank you very much, Pam. We have one from Joseph Sue. If I could get you to unmute and answer this one. Sorry, I'll have you chopping and changing with muting and unmuting, but just as they come in. So when using roof shield, is there a difference between the different types of timber sarking boards, i.e. can I use plywood?
Okay, yeah, so like this is a question we get asked quite often. Sarking boards in general tends to be a Scottish practice. You perhaps see it in the north of England as well, but not much further south. Roof shield can be used over all types of sarking boards, but there are a few differences. One of the main types, most traditional type, is your softwood sarking boards, which are timber planks, typically 150mm wide. These tend to be more permeable, but they have shrinkage gaps as well, so you do get airflow between the gaps and between the boards. So roof shield can be used in that situation in warm roofs, cold roofs, and room in the roof or hybrid roof design that we saw earlier without the requirement for additional ventilation. The other type of sarking that you do get is your sheet sarking, which tends to be plywood or OSB, for example. And these are large sheets. They're less permeable, so there is a wee bit more restrictions on these. Warm roof design, where the insulation is pushed hard up to the underside of the sarkin, continuous from eaves to ridge. Again, no requirement for any ventilation. If you are looking at cold roof design with this type of sarkin board though, you do have to ventilate in the traditional manner.
Okay, great. And Sue, if I can just ask you another one. Callum has said, and this was one that came in via email earlier, I've installed a breathable underlay on my roof, not roof shield. But since installing downlighters, I seem to be seeing condensation on the underside. Is this normal?
Okay, yes, so there's a couple of things that you have to be careful of here. Firstly, you have to understand the performance of the underlay that has been used. Make sure obviously it's permeable and it's suitable for that application. Roof Shield is obviously the market leader in pitched roof underlays, and it's both air and vapour permeable. So this allows the Roof Shield to be used in pretty much all roof constructions without the requirement for ventilation. In terms of the downlighters, again, what you have to consider is that, first of all, hopefully you've had a nice well-sealed ceiling. Putting the downlighters in, you're basically cutting a hole in that ceiling, so it's an easy passage for uncontrolled vapour to be able to enter into the roof space. If downlighters are a requirement, the best way to do is actually to create a separate service cavity to accommodate those roof lights, and perhaps consider things like vapour-tight hoods and seals, etc., just to reduce the effect of that uncontrolled vapour passage.
Okay, that's great. Thank you very much, Sue. Ian, if I can come to you for a couple of questions, please. Adam has asked, is a high-performance rigid PIR board better suited between the rafters than a flexible mineral fibre?
Okay, good question, Adam. A number of years ago, somebody asked me that very same question. And I'm still puzzling to actually think what the right answer is. Theoretically, the PIR rigid insulation board would be better. So therefore, if we did a U value calculation, you'd need less insulation to get a better U value. But in practice, sometimes the rigid insulation board can be hard to install. I go back to my student labouring days, and I used to get the job of putting the insulation in, and it was a lot easier to put the mineral fibre in between the studs than the insulation rigid from a fixing point of view. So you got it done a lot quicker. With a mineral fibre, you can get it more snugly put in between. So it kind of, the big quandary is a higher performing insulation with gaps better performing than a poorer performing insulation that's tightly fitted? I guess really the main question comes down to the installation. If it's well installed, both will be good. But if you poorly install it, just as the webinar showed, it's not convection tight, the rigid insulation cannot be as performing as it should do.
Okay, that's great. Thanks, Ian. Jessie has asked, and I think I actually remember this question. So in a previous webinar, the question of hybrid roofs was raised, and obviously we've just been chatting about it here as well. So hybrid roofs was mentioned. Is this the same concept?
Yeah.
Clarity around it for them.
Yeah, I'm glad somebody's raised the hybrid roof. I was on the webinar the last time where the question kind of snookered us all as to what exactly a hybrid roof is. And we had a big debate afterwards about what a hybrid roof is, and probably some heated discussions as to what everybody thought a hybrid roof is. But certainly, I think the consensus was that the hybrid roof we were asked a couple of weeks ago was more related to flat roofs, where the insulation's in between the rafters and then some over on top, which is a difficult question. And I think that's the reason we were asked that question, is to the balance of the insulation above and between is very important. And also, where do you put the insulation is a difficult question as well. So I think that's why we were asked that one. On today's presentation, when we're talking about a hybrid roof, we're talking about more of a room in the roof, where you've actually got, as the name suggests, a room in the roof, and you've got small voids, and then on the coombs, which I think is more of a Scottish word, on the slopey area in your roof, that's very tight, and that's more like a warm roof construction, and then you've got the cold roofs either side. So that's what we mean by a hybrid roof. So it was a different concept to the one that we talked about a couple of weeks ago. So that's what we mean by a hybrid roof in terms of a pitched roof today.
And just to clarify, the slopey bit is the technical term for... No,
Yes.
I'm really kidding. Good.
Sorry.
It's fine. And Ian, Dave's actually said, interested to understand issues with granite buildings with ventilated cavities behind the lath, so airflow from SOM to loft, and then insulation of room in the roof in traditional buildings. You might need to ask for a bit more information. Is that one? Do you want to clarify what you might need to answer that, or can you answer that?
Yeah, it's another good question from Dave. I think Dave asks us always a good question in the webinars from ones I've been at. Yeah, it's a good question. The ventilation there between the solid wall and the lath is questionable whether you should have any air movement there anyway. I'm not particular. We would like more details as where the insulation is in there. Is it going to be perform like a solid traditional sandstone solid wall? Certainly from an air movement point of view, I have seen in roofs before where there has been problems where the cavity of a cavity wall has not been closed properly at the top. And that has led to moisture coming into the cavity and bringing up moisture into the loft. And because it's not been closed, you've created the moisture load inside that cold roof that the roof structure has not been designed for, and it's led to condensation problems within it. Now, that wasn't with obviously a roof shield roof, but it was a problem that we were asked to come and have a look at. And it was this moisture driving up, which would be a risk on the granite that Dave's mentioned there. So we'd probably like more details. I think I would probably want to try and close off that air movement and reduce it to acceptable levels.
Okay, good. Really good question here on wind uplift, Pam. If I could maybe come to you. Sorry, just put you on the spot during a sneeze there. Good. So Mark has asked, what do I need to know about wind uplift with roof shield? Can I use it on my project? So do you want to just give a general quick overview and some of the key points that he should be thinking about?
Yeah, sure. So really when we're talking about wind uplift, we're probably looking about the effects of it in an unsupported, the membrane in an unsupported application. So for example, draped across open rafters. So BS5550, the Code of Practice for Slating and Tiling, does set out how each manufacturer must test and display the criteria and how the membranes perform. So in all our literature, sorry, the guidance we have, all the user guides that go out with every role, you'll get a map of the UK broken down into the different zones, and then the tables of our actual test results there. So you would firstly look at checking where you're positioning. So if you were in Southampton, you'd be in zone 1, for example, and Thurso, right in the north of Scotland, other extreme, you would be zone 5. So we test the roof shield with different batten centres, and we've also tested with slate zone sarking as well, because that's a common use for roof shield up here in Scotland. So most of the UK falls into zones 1 to 3, and you don't have to take any special consideration there. You don't have to worry too much about your batten centres. They can be easily up to 450 mil and above. If you were north of that, if you were in zones 4 and 5, then really all you need to do is look at either reducing your batten centres down to 245 or above, or looking at taping the roof shield or using a counter batten. In all cases, you should look at supporting and sealing off that overlap, so locating it underneath a underneath a tiling batten, so that it doesn't sort of pull open, and that's considered good practice under 5534. And then if you're going with softwood sarking, traditional Scottish, you're good to go for all zones.
Okay.
But any questions and specifics, give us a shout again in technical.
Good. Okay. And actually, Pam, if you just answer as well, Niall's asked, do I need to tape the overlaps in roof shield? And we're obviously talking about taping there. What do they need to be?
Yeah, no, that's a good overlap, a good crossover there. You don't have to use to tape the overlaps in roof shield. It's one of the key benefits of it, as long as you make sure you follow good practice by ensuring that overlap coincides with a tiling batten. It may be that sometimes some people do want it if you're in a very exposed situation, or you're concerned about anything getting underneath that. Your overlaps are dictated by your pitch and whether it's supported or unsupported. Again, our user guide has tables to guide you through that. And very handily, each roof shield roll is printed with a 150 overlap, which does the majority of situations. And your vertical overlaps, where you lap one roll to join on with the other, needs to be a minimum 100 mil and centered over a rafter. So saying that you don't have to tape it, it's there, but if you do want to tape it, our wrap tight tape is the perfect partner to go with the roof shield, because it's vapor permeable. It's going to allow vapor to pass through, and it bonds really, really well to roof shield, because most tapes don't stick well to roof shield because of its hydrophobic nature.
Okay, lovely. Thank you, Pam. Sue, if I can come to you for a couple of questions, that's okay. Joe has said, I've specified fiber cement slates, as I was under the impression ventilation was not needed with roof shield. I've been told this is incorrect.
No, it's not. It's not incorrect. Roof shield is designed to be used without ventilation to the roof space. However, if you are specifying a tight fitting outer covering, it's important to take that into consideration as well. Ventilation of that batten cavity is unrelated to the requirement to vent the roof space with roof shield. And that requirement is usually the recommendation of the slate manufacturer. And typically, whatever is required there would be required regardless of which membrane is used anyway. So any vapor permeable membrane, you'd have to treat that batten cavity the same.
Okay, another question we get asked quite a lot actually from Paul Sue. Are the likes of roof shield and wrap tight considered to be waterproof? I want to specify a particular tile, however the roof pitch is lower than the maximum allowed for the tile. Do I double up the membrane?
Yeah, we do get asked this one quite often actually.
Yeah.
Any pitched roof underlay other than bitumen felt, for example, would be classed as being water resistant, not waterproof. So the primary water holdout of that building has got to come from the outer covering. And if it's unable to provide that function because it's not suited for the pitch that it's being used at, for example, then what you do is you're then relying on the membrane to overperform, to perform above its normal specification. So membranes are secondary protection, your outer covering is your primary protection. Yep.
Okay. That's great. Thank you very much, Sue. And Ian, if I can come back to you for a couple of questions, if that's okay. The NHBC and BS5250 show a ridge-only ventilation for cold roofs. I thought it was advised against only having ridge ventilation.
Yeah, that's a good question. Certainly in days gone by, it was always frowned upon to have ridge-only ventilation, and indeed the ventilation manufacturers themselves used to say not to have ridge ventilation only, and it should always be supplemented by eaves ventilation as well, to avoid this suction effect. However, now it has been deemed that a ridge ventilation system is okay. And that's more because the air tightness and convection tightness of the ceiling prevents that suction effect, and you can get more air movement through the ceiling when you're using an LR underlay, an airtight one, you should have that ridge ventilation, high level ventilation. So yeah, it certainly was frowned upon, but if your ceiling is convection type, it can be okay. One of the things you've got to be careful, as it said in the seminar, was that if you are using ridge ventilation only, remember that that ridge is open until such time as you've got both sides of the roof tiled and you have your ridge tile in. So therefore, it will not be watertight until the very last minute when you put that ridge tile on. So the roof is exposed for longer and it's never airtight.
So generally, how long is that roof left exposed for if you're putting ridge ventilation?
That's a bit of a debatable one, and I think that if there's many roofers listening to this, they would say it will depend when the tile manufacturers will get us the tiles in time. So it's very difficult to tell that. I mean, it doesn't take long to tile in a roof, especially if you're using the concrete tiles. They can be very quick. A couple of days could put that on quite easily. If it's natural slate, it might take a bit longer because there's a bit more craftsman involved in that. Mm-hmm. But generally, I was being a bit flippant there, but the tile manufacturer's delivery time is probably going to dictate how long that roof's exposed.
Okay, good, thank you. And Jack has asked, why would the condensation risk be different in a warm roof than a cold roof?
Yeah, it's a perfectly understandable question as well. You think, well, because they're both roofs, why is the risk different? The risk's different in a warm roof because in a warm roof, you're really only dealing with small voids, if at all, any voids. So the underlay, between the underlay and the insulation, there might not be any voids at all. And more traditionally, there's at least 50 millimeters of void. But that's not big in the scale of compared with a cold roof, which has got a much larger void. Now that much larger void creates a bigger area between the temperature drop from inside to out, and therefore that area can create more condensation within it before it's released into the environment outside, which is where you want that vapor to escape before the dew point. So there's different risks in the different types of roofs, and that's why we have to deal with them differently and take that into consideration.
Okay, thanks, Ian. Pam, I'll come back to you. I've got about 4 or so questions left, so I'll split it between the 3. Okay. So Kenny has asked, I'm building a house and using a SIPS roof. I know a bit about that, obviously, from my own home. I've been planning on using roof shield, but would RAPTYPE be a better option? Oh, you're muted. Sorry, Pam.
Sorry, getting over enthusiastic there. Yeah, I mean, roof shield's fine to use in a SIPS roof, but there are some definite benefits to using RAPTYPE. One being the possibility of being able to pre-apply it in the factory before it's shipped to site, so you're actually protecting the panel during transportation. The major one is probably that the RAPTYPE will definitely help to enhance the airtightness of the building. In a lot of situations, SIPs are utilised because people are looking to maximise the energy efficiency of the building. And either reach passive house standards or zero energy buildings. So really things like RAPTYPE and increasing the air permeability or decreasing the air permeability, so keeping it nice and airtight is a real key benefit to it. And also the use of RAPTYPE being airtight means that you're not running the risk of wind washing, sort of air getting into those panels or bypassing through the gaps if people haven't been quite so good in the tolerances. So yeah, roof shield, RAPTYPE, over roof shield does have some key benefits for that type of scenario.
For that particular application, yeah, certainly that's what we use on our SIPS roof. We use the RAPTYPE mainly for that reason. We were going for low air tightness in the home, and having installed it myself now with some help. Yeah, just a big advocate of that for the application.
It certainly helps, because otherwise you might have to consider trying to link your wall into a vapor control layer, which it's very difficult to do detailing wise.
Yeah, absolutely. Good. Another question from the same chap. Can I leave the underlay exposed prior to fitting my outer covering?
Yeah, it fits in with what Ian was saying earlier on as well. It depends on when the tiles get to site. But also during lockdown, there's been a lot of sites not progressing or slowed down because of that.
Mm.
It is always good practice to keep that exposure to a minimum before you get your primary water resisting water shedding layer on. Normally we recommend between 3 to 4 months for membranes exposure, but that's really relating to the UV resistance to the membrane rather than more the suitability of them being left open. However, we have to take into account we live in an island. Some parts of the UK are a lot wetter than others. And sort of wind-driven rain can be a factor. So really it's best practice to try and get it covered within as soon as possible, or within 3 months' time. If you know it's not going to happen and you are expecting adverse weather conditions, then consider putting a temporary protection up there just to add. More in the winter than this time of year, though.
Sure. Okay, that's great. Thank you very much, Pam. Sue, we won't let you off without one more, I don't think. One from Chris. Is a vapor control layer required in warm roofs?
This is one of the questions that you answer with it really does depend. Depends on other factors such as we're hearing, like the insulation type, how well it's fitted, etc. Are the joints sealed? If so, it may not need a vapor control layer. What we can do is obviously we can look at the construction, we can run some calculations, look at it, and then give advice as to the correct procedure to go forward, whether you need one, whether it's not necessary or not. So we would do that on a project basis.
Okay, good. And on the YouTube feed, George has asked Sue, and I can stick with you for another one. Building paper traditionally was used to provide moisture-resistant and breathable membranes externally behind vertical rain screen timber cladding. Which of your products can be used for this?
I do actually remember a building paper that we did actually used to supply. Obviously, technology's moved on since then. We have various membranes that can be used in this application, and a lot of it will depend on the requirements. So we have a reflective membrane which will help improve the thermal performance of a building, of the wall. Depending on whether the cladding is open jointed, you might need something that has a bit more UV resistance. So we have a facade membrane called Facade Shield, which can be used with open joints. So we have a solution that has moved forward from the old paper days. Good.
Yeah, things evolved, don't they, and changed. I remember breather papers actually from when I was in internal sales. So yeah, right, good. Okay, and Ian, I think I've got one question left, I think, actually. If I can just finish with you, if that's okay. And if anyone has any last minute ones, please post them now. There's one there from Sam O'Herg-Bosna. Sorry, and I think if you can email us with this so we can get a little bit more information regarding the type of insulation spec that's being proposed, etc. If that's okay, we won't answer that one here because I think we just need a bit more detail. But we do have a question from Lily asking, what is the main difference between Wrap-Dyte in comparison to Roof Shield?
Great. I was hoping I was going to be asked that question, and it's opportune that I'm in the office at the time.
You've not got props. Yeah. Oh, good.
So we have Roof Shield here. So the main difference is that the air tightness of the Wrap-Dyte compared to the air permeability of Roof Shield. As I say, it's great that I've been asked that question. I was hoping we were going to ask something like that. So we've got the Roof Shield there, and you can see that it's watertight, but we can pump air through that quite easily, showing its air permeability. And that's why it's really good for cold roofs, because it lets that air movement in that large void, which we spoke about earlier. And for the wrap type, we have it here, and we're trying to push air through that, and it's a lot tighter to get air through that. Still vapor permeable, but it's a lot tighter to get the air through. So going back to the question that we were asked earlier about the warm and the cold roofs, for a warm roof, the air tightness is quite important because you don't have the air gaps that you do with the cold roof. So wrap tight is a much better option because also the insulation is fully supported, usually supports the underlay. The wrap tight can be installed perfectly on top of the fully supported insulation, and the roof shield is perfect for the cold roof where you've got that large void and you want that air movement throughout that large void. So thanks very much for the question, because I'm now able to use those props, and I'll put them away again till the next one.
Just to add to that, Ian, actually, for people that aren't as familiar with wrap tight, worth mentioning, obviously you have the difference in terms of the air permeability, roof shield, airtight, wrap tight. The other main difference with wrap tight is obviously the self-adhesive nature of the product. So there's not really any other membranes used in these type of applications which are, breathable, vapor permeable, and self-adhered, right?
Absolutely, yeah. The adhesive is quite important on it. And just to make sure that I have taken the release liner off this, we can show it with the adhesive sticking this hold. Obviously, it's very easy to have the water tightness if you have not taken the release liner off. But if you don't take the release liner off, you don't have the permeability, vapor permeability in the long-term performance. Good.
Okay. Thank you very much. Well, I'm not seeing any other questions. So I just want to thank everyone for attending. Sincere apologies about this morning. We were all set to go, and just one of those things that couldn't go ahead. But I'm really pleased with the turnout was still so good based on the change of time. And I hope you've enjoyed it, having a nice cup of tea or a gin and tonic or whatever you fancy at the end of the day. And it's actually quite nice to finish the end of the day with this webinar. Actually, it's been good. So we really appreciate all the questions and all the feedback and you attending. I went through previously, you'll get this follow-up email. You can watch the replay, circulate the replay. Please fill out the feedback form if you have time. We really do read them and value any feedback that you give us. And don't forget to visit that Proctor Group webinar page. So if you go to www.proctorgroup.com/webinar, you can actually register there now for our webinar in 2 weeks' time, which is on Friday the 21st of August at the usual 10 a.m. time, which will be air gels in building refurbishment. So you can register for that now. And there's also a raft of other stuff you can do on that page in terms of requesting a literature and sample pack about these products we've been discussing. You can request a meeting with one of these guys or one of our wider team who are all working from their home offices, supporting various architectural contractors and our customer base. Samples, if you go there, you can basically do what you need to do on that page. And of course, you can contact us by phone or email or however you like, really. If you can, please give us a thumbs up on the video. It helps us with views in the future, and also it lets us know you like it. So that's good. And if you wish, then subscribe to our channel. We do from time to time upload new content that isn't just webinars, which you might find of interest. So that will then appear for you to watch in your leisure. So I think that's it. Thank you very much to the marketing team. Graham could have had a sleep in this morning. He was up until the early hours finalising this webinar. They are done, from scratch, and they're done by our in-house team. So there's a lot of effort that goes into them. So thank you to them, and thank you very much to the panel. Great to have you here answering the questions, done very proficiently as well as always. So thank you. And we will see you in 2 weeks at 10 o'clock, hopefully.